Okay, so good evening, everyone. I am Moina Ghoshal. I am a PMRF and a research fellow at Indian Institute of Science Education and Research, Kolkata. And I have been assigned as a TA for this course entitled as Fundamentals of Spectroscopy, which was instructed by Professor Sayan Bakchi and Professor Anirban Hajra. And this is the assignment related questions for week 5, where I am going to discuss some questions regarding these lectures from 22 to lecture 26, where which will be beneficial for you to solve problems related to that lectures. And also, since it is a live session, so you can ask me any questions. So moving on to this material, first of all, I need a very brief repetition of the previous class or two classes what we have discussed. So, first of all, if you can remember, in the previous class, we have discussed about rotational spectroscopy. In last two classes, we have discussed about rotational spectroscopy. So, what is rotational spectroscopy? Because molecules have rotational energy levels, and under which condition rotational transitions will happen. Anything about rotational motion. For this, we need to consider that angular motion. What is angular motion and how it is related with the linear motion was discussed. That for every individual in the linear motion, there is something very similar in the angular motion, right? And for this, then from then the concept of moment of inertia was established also. And then the calculation of rotational energy levels was done, and there was the introduction for these rotational quantum numbers. And then it was discussed that under which condition a molecule will be microwave active, and it was shown that molecule should have a permanent dipole moment. Should have a permanent dipole moment. That's why it was also shown that homonuclear diatomic molecule where there is no dipole moment between the atoms, or there is no dipole moment, and hence they are rotationally inactive. But heteronuclear diatomic molecule which has a permanent dipole moment, they are rotationally active. And then there was a discussion on the selection rule for rotational spectroscopy, and it was discussed using the concept of transition moment integral. What is transition? What is the concept? That if I am writing with bracket notation, that if there is a transition from psi m to psi n, psi m mu psi m will be non-zero, not equal to zero. This is a condition for transition moment integral. And it was also discussed that for a transition to happen, this transition moment integral should be non-zero. Whether it is an electronic transition, vibrational transition, or rotational transition, your transition moment integral should be non-zero. And then it was a spectra of uh, CO molecule was discussed, where there was some small peaks along with the normal peaks that was coming in the rotational spectra, and it was discussed that this is the effect of isotopes, and the intensity of the peaks, the small peaks that have appeared, and it was because of coming from the abundance of the isotopes. The more the abundance, the more intense the peak. Then there was a discussion for the concept of degeneracy. What is degeneracy? And then these were the discussion for this quantum number mj, and it was discussed that how it is related with the degeneracy of a rotational level. It was discussed that degeneracy will be given by 2 into j plus 1, where j is the rotational quantum number. And then it was seen that this degeneracy is present when there is no electric field or any magnetic field. But when there is electric field, this degeneracy is lifted, and it was broken into its several components in presence of external perturbation, which was discussed as Stark effect. Okay, this was a Stark effect. And then there was a discussion on factors on which intensity of this rotational line depends. It was shown that there are two factors on which intensity of this rotational line depends. One is transition probability, and another is population of initial state. Okay, so for rotational transition to happen more intensely, you need to satisfy two conditions. First of all, your transition probability should be there, should be non-zero, that your transition can happen. And secondly, you must have the population, more number of molecules in the initial state. Then, and all of this was discussed in the concept of rigid rotor, that is, the bond length is fixed. But how all of them will change in presence of non-rigid rotor, where bond length can change due to vibration. And then there was the concept of centrifugal distortion. Hmm, yeah, concept of centrifugal distortion. The how it is, what is centrifugal distortion, and how non-rigid rotor approximation gives all the necessary values that we have obtained already from simple harmonic oscillator approximation. It was shown. And then there was a discussion of moment of inertia along different axes, and from that different types of molecules were taken, different types of molecule which are present and who they under which category they are going. This was also discussed, and there was a discussion about these three different types of molecule. One is spherical top, another is symmetric top, another is asymmetric top. Okay. So there was a discussion on these three different kinds of things: spherical top, symmetric top, and asymmetric top. And from symmetric top, it was shown that it could be of two types. One could be prolate, one could be oblate. And under which category they are falling, the molecules are falling. It was also shown that under which molecule will go for prolate configuration, which molecule will go for oblate configuration. It was also shown. And then there was a calculation for moment of inertia of this OCS molecule. This was shown also for this OCS molecule. How is the moment of inertia? How we need to calculate it? This was discussed. And then it was a proof for the water, that it was shown for water that how why it is asymmetric top, because in case of water, considering the bond angle and bond length etc. values, it was shown that the moment of inertia along different axes are different. That IA is not equals to IB, which is not equals to IC. That means it only satisfies the condition for asymmetric top, so water was discussed as a asymmetric top molecule. Then finally there was a calculation for this selection rule for this rotational transition, and this was shown the condition of the concept of Legendre polynomial. Legendre polynomial. What is Legendre polynomial? They shown, you have seen that there was a function for theta and phi, and this theta function you can write in terms of some polynomial which was named as Legendre polynomial. So all of this was discussed about rotational spectroscopy. From the very first for the first two classes, there was a discussion on spectroscopy, how it is evolved, what kind of spectroscopies are there. It was all discussed, and in the last couple of classes it was discussed about rotational spectroscopy. Now we are moving towards some more another type of spectroscopy, which is vibrational spectroscopy, and this was discussed in some 5 lectures which I will cover today. So in the lecture 22 there was first mentioning of the what whereas the IR regions in the electromagnetic spectrum. Yeah, what is whereas the IR regions in the electromagnetic spectrum, and it was also discussed in the previous classes that in the I couldn't remember exactly which class it was discussed, that this IR related the IR energy zone or infrared energy zone for this electromagnetic spectrum is responsible for vibrational transition. And for this, in IR region, there are three different types of IR regions was discussed: near IR, mid IR, and far IR. There will be a question regarding this, which I will discuss then. And then there are the discussion on Hooke's law. You have learned in physics also this Hooke's law, and how, and there is a model of simple harmonic oscillator model. Sorry. And then there was a concept for the change of the shape of this parabolic potential energy curve with force constant. suppose what is force constant, it was also discussed, that there was the equation of 1 by 2 pi root over a by mu. This was an equation where this k is denoted as force constant. So how this force constant actually affects the potential energy curve for this harmonic oscillator, it was already discussed. Next, in the next lecture, there was a mathematical proof for the dependence of this force constant on this potential energy, and it was shown that this force constant k is related to the potential energy by this equation, that it is the second derivative of the potential energy at R equilibrium. Okay, so where is R equilibrium, that was also discussed, that is the equilibrium bond length when there is no vibration. But as you are vibrating, suppose this is a bond, then I am stretching, bending, different kinds of motion I can produce so that this bond will vibrate. So what will be the bond length will always change. So this will be denoted as R, and then it was shown that this K depends upon this second derivative. And there was a calculation for the energy of this harmonic oscillator. And it was shown that this energy EV will be V plus half H nu. It was shown the energy of this harmonic oscillator, that this energy will be EV equals to V plus half H nu. And then there was a calculation of energy difference between two successive vibrational levels and 0 point energy. So what was the value for the difference between two successional energy levels? It was H nu. We'll come to any problem for this, and also the 0 point, what is the 0 point energy, it was also discussed as half H nu. So it was shown that for case of simple harmonic oscillator, so for the case of simple harmonic oscillator, 0 point energy is shown to be half H nu. What is 0 point energy? 0 point energy is the energy of the ground state, okay, for the vibrational transition. Now you have seen that for rotational case, you have seen what was the value of this ground state. For j equals to 0, what was the energy? Energy was 0. But for vibrational case, energy is not 0, it is half H nu. Next, there was a discussion for the selection rule for vibrational transition. Selection rule for vibrational transition. And there was two discussion of gross selection rule and another was specific selection rule. What is gross selection rule? Gross selection rule states that your d mu by dx will be not equals to 0. That means you need to have, you just think of your previous case for rotational transition, you need to have some condition like your molecule will need to have a permanent dipole moment. But here, no such condition is there. The condition will be changed, and the new condition for this IR transition is your change in dipole moment will be non-zero during vibration. That means when you are vibrating a bond, your dipole moment needs to change. Another specific rule is your delta V, that is the vibrational energy level between difference between vibrational quantum number, should be equals to plus minus 1. Why it is coming? It was also discussed that why this is coming so for plus minus 1. And also there was a derivation for the selection rule from the transition moment integral. What I have said here now. And then there was a concept for fundamental transition. What is fundamental transition? Fundamental transition is transition from ground state to first excited state. V equals to 0 to V equals to 1. This is called fundamental transition. And in the next lecture, there was shown that there are in the actual case for in the actual vibrational spectrum, you can see that more than one lines are present. More than one lines are in the vibrational spectrum. So why this is coming? Because this is coming, this can be explained in the concept of anharmonicity. In the earlier case, we have thought that the molecule is as a simple harmonic oscillator. Okay, but actually this is not correct. There is a concept of anharmonicity, that up to you can vibrate a bond, a bond is vibrating, but up to certain point, after this point the bond will break. Okay, and there was a concept of dissociation energy. And then there are potential energy surface in terms of Morse potential was given for this anharmonic oscillator. In terms of Morse potential, that is for the case was like this. We have seen that this actually belongs to Morse potential curve. Okay, and then there are the so and then there was a change in the vibrational energy levels of a molecule. It was discussed that how the energy of a vibrational energy level is changing due to anharmonicity. It was shown for harmonic oscillator approximation that the energy level between two energy levels, the energy difference between two energy levels is constant. It is always h nu. But in case of anharmonic oscillator, you have seen that as you are going up and up, or you are increasing this vibrational quantum number, the energy levels are coming very closer to each other. How this is coming? Because there is a there is a term corresponding to anharmonicity. In the next lecture, this was lecture number 26, there was discussion for the shape of this potential energy curve for anharmonic oscillator, and the mathematical form was discussed. What was the mathematical form? Mathematical form was discussed just like the case of simple harmonic oscillator. In this case, it was discussed that this was a 3 derivative, that is G3V dr3. And then there was a discussion for fundamental vibration and overtones. So I have said that what is fundamental vibration? This is V equals to 0 to V equals to 1. And overtones are all other transitions rather than plus 0 to 1. That means 0 to 2, 0 to 3, any other transitions, they are overtones. This is the first overtone, 0 to 2, this is the second overtone, like that. And there was the concept of hot band. This was a transition from the excited state to next excited level. That is, this transition is not happening from the equal to 0 level. This transition is happening from somewhere else in the higher energy level. So this was discussed as hot band. So all of these topics were covered in the lecture, which was very nicely described by Professor um, Sayan Bakchi. So this was all the topics that was discussed, and now I am going to solve some questions which will be regarding this topics. So this is my first question. So which one of the following carries lowest energy? Near IR, mid IR, far IR, or UV? So there is a electromagnetic spectrum I have given already, and from this you can say that in which region is more of energy, which have higher energy, which has lower energy. You can see it. So what should be the answer?
Near IR.
Near IR. Okay. Near IR. Okay. Just marking it. Okay. I'm just differentiating this. This is the IR region. You can see infrared. So I'm differentiating these three. Okay. So my left portion, what is this? This is near IR or far IR?
That is near IR.
That is near IR. Okay. You're correct. That is near IR. This is
Mid IR.
mid IR. And this is only this must be for IR. Now you can tell me that near IR is the lowest energy.
Far IR, sir.
Yes, for
Far
IR
IR
will be
has lowest energy.
exactly, because you can see here this is the energy increasing. Okay, so as you go from this left side to right side, your energy is gradually increasing. So This was also discussed in lecture number 22 that the energy levels in the IR region can be written as this order, that UV, yeah, this is the UV region, it will have more energy. Next will be NIR region, that is near IR region. Next will be mid IR region, and this will be very low in energy, because you can see your energy axis is going from left to, it is increasing from right to left. So your left side will have more energy than the right side. And in the topmost side among these four, there is this far IR region. So your answer will be far IR region will be the lowest of energy. Got it?
Yes.
Okay. So this is the next question. Okay, so in a simple harmonic oscillator system, if we decrease the force constant, which of the following will happen? Suppose, what is the force constant? It is denoted by what alphabet? It is denoted by K, right? So the question is, suppose for a simple harmonic oscillator system, always in case of vibration, solving any problems regarding vibrational or energy or vibrational spectroscopy, you must always think of that if it is simple harmonic oscillator model or anharmonic model. Okay, so you had it is said that it is a simple harmonic oscillator system, and it is said that if your K is decreasing, that is, if we decrease the force constant, what will happen to your bond length, and what will happen to your potential energy curve? So what should be the answer?
The
This bond
bond
length will
will be
increase or
weaker.
decrease? Huh?
The bond will be weaker.
Mhm. And the
And
potential
the
energy?
parabola will be smaller.
Shallower. Okay. Okay. So you are saying that bond will be weaker and potential energy curve will be shallower, right? That's what you have said.
Yes.
Yes. The bond will be weaker. The parabola will potential energy parabola will be shallower. So other any other answer? Okay. So this is the Taylor series. You have seen that in the lecture number 23, there was a discussion for Taylor series expansion of this VR, that is the potential energy, and it was shown that the first terms or first two terms, suppose I am doing it here, your VR, it was discussed about this VR about this R equilibrium can be defined as V equals to R equilibrium. First term will be 1 by 1 factorial. This will be dV by dr. This is the Taylor series expansion. R equilibrium, R minus R equilibrium. The sixth term will be 1 by 2 factorial d2V by dr2 R equilibrium, R minus R equilibrium whole square. And then it was also shown, and there is a higher terms are there. I'm not writing that because mainly this part is much more important for me here. Now you have seen that potential energy at equilibrium position is 0. And also this term, this is also 0, because you know that at R equilibrium you need to find what is the value of dV and dr. You know at R equilibrium this potential energy will have a minimum. And you know also that for minimum, this potential energy value will be, the first derivative will be 0. So this term is also 0. So what is the remaining term? And if I neglect other higher terms, the term will remain as half d2v by dr2 at r equilibrium. This is r suffix equilibrium, and this will be r minus r equilibrium whole square. Right? Now you can compare this with this equation of normal potential energy V equals to half k x square. Now you know this x is nothing but this r minus r equilibrium. So comparing these two equations, we can write this one. So comparing these two equations, we can write this k, sorry, this k is equals to d2v by dr2 at r equilibrium, right? So this, comparing these two equations, we can write this. Okay. Now the main thing is coming. Now you have to question the answer. You have to answer the question that what should be the change in the bond length and what should be the change in the potential energy parabola. So first of all, I'm going one by one. Suppose, so what is K? First you need to understand K is denoted as force constant. So this name is not telling anything. What is force constant? We need to understand this meaning. This K is the force constant. Now what is force constant? Or what does it suggest if K is large, or if K is small? What does it suggest? K actually signifies up the force up to which you can stretch a bond. Higher is the value of K, that means it is very difficult to stretch a bond. If lower value of K is there, that means you can easily stretch the bond. Now you can see, you can just think of that in suppose you have in organic chemistry you have learned single bond, double bond, triple bond. Now can you tell me which bond is very easy to just expand or very easy to stretch? Is it single bond, double bond, or triple bond? Very easy to stretch.
Single bond.
Single bond, exactly. So how it will be force constant? It will be low or high for other compared to this double or triple bond?
Low force constant, sir.
Exactly, because you will need very less energy to stretch this single bond rather than double bond, rather than triple bond, right? So you can see that for single bond you just need very less energy because its force constant is very low. Now you are seeing that your force constant is decreasing. That means your bond, suppose there was a triple bond, it is becoming single bond. Now you can tell me if the bond will be stronger or weaker.
Stronger.
From triple bond to single bond will be stronger or weaker?
Stronger.
Stronger. What I have said that this K is the force constant. So, and I have also shown you that you have also answered that for K single bond, K is less. That means there is very easy to stretch a single bond compared to the double bond or triple bond. Now you can tell me which one you can easily break, the single bond or triple bond.
Single bond is easily to break, sir.
That means single bond is weaker or stronger?
Weaker.
Weaker, exactly. That means single bond is very much weaker. So if your K is less, that means you need very less energy to stretch the bond. That means the bond is always weaker bond. So the first answer is what bond length will increase and bond will be weaker. bond length increases, bond weaker. Now the main question is, what should be the nature of this potential energy curve? So I am showing you this drawing rather than drawing it of myself. You can see here that increasing k, that means suppose that you have a potential like that, and it is gradually getting stiffed. Okay, so if you are increasing this k, that means if you are bond making your bond much more stronger, then your this parabola will be very much narrower. That means it will be much more steeper. But if you are decreasing your k, the parabola will get like this. So for low k or decrease of k, so if your k is decreasing, your this second derivative will decrease. That means you will have this kind of shape. That means this will be much more shallower. Okay. So do you understand the difference between this stiff and shallow?
Yes, sir.
Okay. For just a simple clarity. So which one is steeper? This green one or red one? Steeper?
Red one is preferred.
Red one is steeper. This what is this green one is steeper or shallower?
Green one is stiffer and red one is swallower, sir.
Exactly. It is shallow. Sorry, shallow. I'm right. Swallow. Okay. So this is stiffer. This is swallower. Stiff means uh, suppose suppose a mountain or your rock. Suppose you are you'll see you have rock climbing. This is more steeper. Rock is more steeper. Okay. Shallow means you have much more surface, or you may can you have this. This is much more expanded. So this is shallower. But for steep means this is coming very close. Okay. So now you can just define this. What is steeper, what is shallower, and you have seen that for k, as k is decreasing, your bond, your derivative will be decreased, and this will be become much more shallower. So the correct answer will be the bond will be weaker. Your answer was correct. I have also explained that the bond will be weaker and your potential energy will be, the parabola will be smaller. Sorry for the spelling mistake and this, yeah, corrected here. Okay, is it okay?
Yes, sir.
Okay, so I'm moving to the next question. Yeah, so it is saying that what I have shared, you can remember that for any vibrational spectroscopy question, you first need to see which kind of model you have to follow. And here it is written as you have to follow simple harmonic oscillator model, and it is very simple harmonic because it's very simple. Okay, and here it is stated that you are changing the reduced mass of a oscillator from mu, and you will it is converted to 16 mu. So what will happen with the fundamental vibrational frequency? So it will increase by 4 times, decrease by 2 times, increase by 2 times, or decrease by 4 times. That means by 4 times or by 2 times, will it increase or decrease? So can you quickly do it?
It will decrease.
Sorry,
It will decrease.
decrease by how much? 2 times or 4 times? To do it? So the reference, because you do it and I'm also explaining slowly. Uh, so you will find the reference in this lecture number 22. So the fundamental vibrational frequency can be related to this reduced mass by this equation. If this is very important equation in chemistry, that your nu will be equals to 1 by 2 pi root over k by mu. So it was also discussed that if there is wave number or nu bar, how you can convert it. So if you have to convert it to nu bar, you just divide this nu will nu by c. So it will become 1 by 2 pi c root over of k by mu, right? Only a c term will be added up. Oh, sorry, multiply will be there. So this is the fundamental vibration frequency for the reduced mass mu. Now I am saying that my reduced mass is changing to mu prime. Suppose then, and my also my I am considering that my force constant is not changing. So my nu will be suppose changed to nu prime. Now what should be my nu prime? I will write it as this nu prime should be equals to 1 by 2 pi root over of k by prime, right? Now I have to find what will happen to the fundamental vibrational frequency. That means with respect to it is already in the question. It's not saying that you need to find that what will be the value of nu bar with respect to nu, that how it is changing with respect to this nu. So for this you need to find this ratio nu bar by nu. So what should be the ratio? Ratio will be 1 by 2 pi root over k by mu prime, and here will be 1 by 2 pi root over of k by mu, right? So this 1 by 2 pi will be cancelled out. Your k, so since all the terms are within this square root, I am writing this one, that in the upper side there is k by mu prime, and in the lower side this is k by mu. This will be just opposite, that mu by k. And I have also told you that this k and k is equal for this system. So your just ratio will be just root over of mu by mu prime. So I am writing this final relation here, that your sorry your new your new prime by nu, it will be mu by mu prime raised to the power half, right? You have got this relation. Nu prime by nu is equals to mu prime by mu whole to the power half. Now what you need to do, you just need to put the value of mu and mu prime. Mu prime by nu is to, this will be mu, and what will be the mu bar? Mu bar is said that it is going to be 16 mu. So I am just writing 16 mu half. I mean, we will cancel. It will be 1 by 16 whole to the power half. So what should be the value? It should be plus minus 1 by 4. But since we cannot take this minus 1 because this frequency cannot be negative, so value will be 1 by 4. So nu prime by nu is coming to be 1 by 4. So now you can do it easily. That what should be the nu prime? The nu prime will be nu by 4. Okay. So your nu prime should be equals to nu by 4. Now what does it signify? Is it decrease, increase, or what? So you can see here,
Decrease by 4 times.
exactly. So you can see here that your nu prime will be decreased by 4 times. So your nu prime, what will be your nu prime? Your nu prime will be 1/4 of this nu. That will means it will decrease by 4 times. So this is your correct answer. So do you understand how I have done this?
Yes, sir.
Did you understand that?
Yes, sir.
Okay, fine. Okay, so going to the next question. So here you have to find which mode will be IR active. There are three different molecules I can see, and for CO2 there are two modes are there: the CO2 symmetric stretch, CO2 asymmetric stretch, NO2 symmetric stretch, and oxygen stretch. So you have to find which of the following will be IR active mode. Can you answer it?
CO2 asymmetric stretch
Mhm.
and NO2 symmetric stretch.
Okay. So you can find also this answer in this lecture number 24, where it was already discussed that which of IR which modes of a molecule will be IR active or which will be IR inactive. It was said that what should be the condition for IR activity? The condition for IR activity is that your this sorry your IR activity is that your d mu by dx should be non-zero. That means during this vibration, your dipole moment needs to change. Okay. So during vibration, your dipole moment needs to change. If it is not changing, then it is only IR inactive. If it is changing, then it will be IR active. Now I am coming to different modes. Then I will explain you why all other modes are IR active or why other modes are not IR active. So this is CO2, right? This is CO2 molecule. So two modes are discussed about the CO2 here. One is symmetric stretch and another one is asymmetric stretch. Okay, for CO2, two modes will be there. It should be, sorry, three modes will be there, but in question here, two modes are actually discussed. So I am discussing about two modes. One should be symmetric stage, another is asymmetric stage. Now I have to find which of them is higher active. That means I have to find in which stretching mode this d mu by dx is not equals to 0. That means your dipole moment is changing with length or with time. Okay. So for symmetric stage, so for suppose this is a dipole. So in the when there is no vibration, what should be the dipole moment of CO2 in the absence of any vibration?
Zero.
Zero, because you can see here that these two types, this is from C to O, this is the dipole direction, another dipole direction is that, and this since these two oxygens are equivalent, so it will cancel out each other. So at the ground state or at the when there is no vibration, your dipole moment is zero. But when you are stretching it symmetrically, that means you if you are expanding it, these two oxygen bond will be expanded in equal amount. If you are compressing it, these two oxygen bonds or two CO bonds will be compressed by equal amount. That means what you are doing to this one bond, you are doing the same thing with the other bond. That means your dipole moment will be not changed, because suppose it is increasing to that much, suppose somewhere at some point of time or at some point of vibration it is like that much, then your other bond will be like the same amount, the same, so it will always cancel each other, so the dipole moment will be zero. So du mu by dx will be zero, so it is IR inactive mode. Now coming to the asymmetric stretching mode. So what asymmetric mode stretching said? Like I have said about the symmetric stage, what should be the asymmetric stage? Asymmetric stage means one bond will be compressed, another bond will be expanded, or it is expanding with different amount. That means there will be no correlation between your two bonds. Okay. So always, if you do the thing that your two bonds are behaving differently, you will always have a net dipole moment. Okay, so you will always have some net dipole moment. That means your dipole moment will change and your d mu by dx will not equals to zero. So this asymmetric stretching mode is IR active
Active.
mode. So one thing also you can see that I have when I was discussing about the what the content of this lecture, then I have told you that for a molecule to show IR activity, your dipole moment needs not to be zero, and no, sorry, need not to be non-zero. That means like just like the rotational energy case, that you must have a permanent dipole moment. Okay, but in case of vibration, you can see initially CO2 molecule doesn't have any dipole moment. Okay, zero. Its dipole moment is zero, but its asymmetric stretching mode is IR active mode. That means for IR activity, you don't need the molecule to have a permanent dipole moment initially, but there should be a change in the dipole moment. Next, sorry. So next, I am coming to another molecule, which is NO2. So what should be the structure of NO2? It will be just like CO2 or anything else.
NO2 has band structure
Band
like
structure.
H2O.
Yeah, you do also have a linear structure, but also now. NO2, yeah. Confusing with NO. Yeah, okay. Is this correct? I have drawn is correct
Yes,
or
sir.
not? Yes, because what I have written that this minus charge is delocalized using these two oxygen atoms. Either one would be negative, one will be positive, one will be one will be double bond, another will be negative. So it is delocalized between these two oxygen atoms. Now what should be its dipole moment? Its dipole moment will be always directed from this. Okay. Will they cancel each other? No, because this is in case of CO2, they are just linear molecule. So one plane, this is another plane. This is the dipole moment in one plane, and this is the dipole moment in the same plane but opposite in direction. So they will cancel out each other. But it is not the case for NO2 molecule. This will not cancel out each other. So in case of NO2 molecule, and suppose I am doing symmetric stretching, so upon symmetric stretching, its d mu by dx will be not equals to zero. So it is also IR active mode, right? So if you are doing symmetric stretching to NO2, the to NO bond symmetrically stretch, the dipole moment will change because it is a resultant of these two different dipole moments. So it will be also IR active. So I have got two higher active modes. That one is I am taking it, giving to it. That this is not higher active. This is higher active. This is another higher active. Now comes to oxygen. So oxygen will be higher active or not?
No, it is not IR active.
Why?
It has symmetric spreads.
Hmm?
It shows symmetric spreads. No?
So
From any side we pull it,
hmm.
it will remain. It will not change the dipole moment.
Why you do not change the dipole moment? If you are increasing the distance,
Linear.
then your
O2
dipole
is
moment change.
linear molecules.
Sorry.
It's a linear molecules.
So suppose I have a linear molecule like CSO. So is it suppose I have this molecule. So dipole moment is zero here?
No, sir.
No, because these two molecules are these two atoms are different.
Atoms are
So
different. Yes, sir.
yeah. So your linear molecule doesn't mean that is always dipole moment will be zero. There is another thing you have you two are missing, that it is a homonuclear diatomic molecule.
Yes, sir.
So yeah, so mu is zero here.
Yes, sir.
There is no charge separation between these. This is homonuclear diatomic molecule O2 N2. So if you stretch it, you bend it, anything you can do with it, its diamond is not going to change because it is always zero. So it is also iron inactive. So we have only two options left. That is the CO2's asymmetric stretching mode and NO2 symmetric stretching mode. Understand? You understand that?
Yes, sir.
Okay, fine. So the next question is, if the fundamental vibrational frequency is at 4000 cm inverse, the first overtone will occur at what strength? It is your question. Will it be more than 8000? At 8000, exact at 8000? Less than 8000? More than 9000 centimeter inverse? So when there is no mention that whether you have to take a simple harmonic oscillator thing or you don't have to take this, then you will go with the benefit of the doubt will go with an harmonic oscillator because this is the real case. Okay, so in this case you have to consider an harmonic oscillator approximation. So what does an harmonic oscillator energy? Okay, so first you try to answer it, then I will tell you. Just qualitatively you can tell me. It's a very qualitative question, and I will show you also mathematically that why I'm saying this. So first, you can tell me. So fundamental vibrational frequency. What is the difference? This fundamental vibration. Another is overtone. Or here it is written as first overtone. So what is the difference? Can you tell me?
Half H nu.
Half is new what? So I am saying you that you have to just what is the difference? Half is new is nothing but the energy just okay. So for first overtone, it is also half H nu. For fundamental vibration, it is always half H nu. For anything, it is the energy of the vibrational level. Okay. So it is the energy. Since it is energy, so it is not related with this fundamental vibration or first overtone thing. first overtone or fundamental vibration is actually related to transition. Suppose from V equal to 0, there is a transition to V equals to 1. That means from the very low ground state, there is a transition to the first excited state. Okay, first excited state is the V equals to 1 state. So it is related to this fundamental vibration. And what is the first overtone? I have said it. That first overtone is the transition from equal to 0 to the V equals to 2 state. Someone is trying to join it. Okay. So this is what I am trying to say, that the fundamental vibration is from V equal to 0 to V equal to 1 state, and your first overtone will be from V equal to 0 to V equal to 2 state. Okay. So suppose I am writing this. First understand it qualitatively, then I will explain it with mathematics. So V equals to 0, V equals to 1, equals to 2, equals to 3. Yeah, do you want to say something? Gumalapati, can you please mute yourself?
Hello, sir.
Yeah.
Hello.
Mhm. Can you please mute yourself? Or do you have anything to say?
Yes, sir.
Okay, so coming back to this one, suppose I have V equals to 0, 1, 2, 3, 4 different levels. Okay, suppose I have simple harmonic oscillator approximation. And simple harmonic oscillator approximation says that the energy difference between your two states will be always constant. This will be equals to h nu. Right? I have said that. This is always h nu. Okay. This is your simple harmonic oscillator approximation, that the energy difference between two states is similar. Okay. So if you find any energy, you cannot tell from which state it is coming from which upon to which energy, because all the energy difference are same. But for the actual case, anharmonic oscillator, for anharmonic oscillator case, I have showed you that as you are increasing this vibrational energy level, or as you are going up, these energy levels are getting close. Okay. So for the same thing, for anharmonic oscillator, 1 equals to 2 equals to 3. So it is getting close. Okay. So actually, what you have said here, that your this transition energy is 4000. So what about this transition energy? Will it be 4000 into 2, 8000, or will it be less than 8000, or will it be more than 8000? What will be the answer? Now you can tell me. Is this question is clear to you, or I'll explain again?
At 8,000.
At 8000. Okay. Okay. So I'm just explaining again. Suppose for this case, suppose V equals to 0 to V equals to 1 transition, what should be the energy? H nu. This 0 to 0 to V equal to 1 is H nu. V equals to 0 to V equals to 2 transition, what should be the energy? This is H nu, another H nu. This will be
2h nu.
2H nu, exactly. So this H nu, Suppose I have said this is for simple harmonic oscillator, it is 0 to 1 transition. So you can see here 0 to 1 transition is fundamental vibration, and 0 to 2 transition is fast overtone. Suppose, so related to this question, you have said that this value is 4000. So what should be your fast overtone? It will be 2 into 4000. That means it will be 8000. As simple as that for simple harmonic oscillator, right?
Yes.
Exactly. Now, for an harmonic oscillator, I have seen that if you are going to increase your quantum number, vibrational quantum numbers, energy gaps are getting close. Suppose this is v equal to 0, this is v equals to 1. Now v equals to 2, v equals to 3. They are getting very, very much closer to each other. Okay. So, if your energy difference, always your fast overtone energy
Less
will be
than.
exactly always less
Less.
than 2 into fundamental transition energy. Okay, I'm just writing it fund so that you can understand. You understand it qualitatively that your energy or fast overtone energy will be always less than this fundamental energy, 2 into fundamental energy. So in that case, you can say that your answer is always less than 8000
Less
centimeter
than
impulse.
8,000.
Exactly. Now we will prove this mathematically. You can find this answer in also lecture number 26 for this, and I have need to explain that what should be the energy for an harmonic oscillator. I am writing this for this new bar is equals to v plus half. Okay, so new time in terms of new bar I will write it because yes, it is given in wave number unit, so I am writing it in terms of wave number. This is new e bar, this is new v. These two are not equal. Okay, next minus v plus half whole square new bar e chi e. So chi e is defined as an harmonicity constant. To find the energy difference between two levels, what you need to do? To find the energy difference between two levels, you need to find the energy of the two levels. You just subtract it, we'll get the energy difference between two levels. So I'm going to calculate the energy for three different levels, because for my fundamental transition from v equal to 0 to v equal to 1, and for first overtone I have a transition from v equal to 0 to v equal to 2. Okay, so I need to calculate this energy for v equal to 0, v equal to 1, and v equal to 2. So I'm calculating it one by one. So you will tell me this new 0 prime, what is for v equals to 0. So I'm putting this v value as 0, so there will be half nu bar e minus, it will be 0, so 1 by 2 only there, 1 by 2 square, this will be 1/4 nu bar e chi e. Now what should be the value for nu 1 prime? That is for v equals to 1. You just put it, you know this mathematics, 1 plus half, this will be 3 by 2, right? 3 by 2 nu e prime minus 1 plus half, this will be 3 by 2. 3 by 2 square, 3 square will be 9, 2 square will be 4. So this will be 9 by 4 mu bar e chi e. Next, I need to find nu 2 prime, so nu 2 bar. Just you put this value of v equals to 2. So 2 plus half, what will be the value? 5 by 2. So 5 by 2 nu e prime minus, now 2 plus half, 5 by 2, 5 by 2 square up, it will give you 24. 25 by 4 mu e bar chi e. So I have three different values of these energies corresponding to v equals to 0, v equals to 1, and v equals to 2. And I am also again mentioning that for if there is no mention that on which approximation you have to calculate, you will benefit of doubt will be with the enharmonic oscillator approximation, unless it is mentioned that you have to calculate it through simple harmonic oscillator approximation. So with this enharmonic oscillator approximation, I have calculated the energy of three different energy levels. Okay. Now I have to find what will be the energy difference. For fundamental transition, what I've shared that you have to find the energy between V equals to 1 level and V equals to 0 level. So you need to find this one, mu 1 minus mu 0 bar. So what will be the value? 3 by 2 mu E bar minus 9 by 4 mu E bar chi E sorry minus 1 by 2 mu E bar minus 1 by 4 mu E bar chi E. Right? So if you take these two terms chi E and chi E, you can see this 3 by 2 chi E minus 1 by 2 chi E. That will be give you only nu E. Sorry, this is not chi E, this is nu E. So 3 by 2 nu E bar minus 1 by 2 nu E bar. It will give you nu E bar. Just. And the second term is, oh yeah, this will be positive because you are this minus this one. So this will be minus and there was a minus, this will become plus. Exactly. So minus is 9 by 4 minus, for clarity I am just doing it. This will be because I am taking this minus common. So this plus will be become minus nu V bar chi E. So it will be 9 by 4 minus 1 by 4, it will become 8 by 4. 8 by 4 becomes 2. So 9 mu V bar minus 2 nu V bar chi E. This is right. So I have found what should be the difference, what should be the value for fundamental transition. Fundamental transition. Now I have to find the same thing for first overtone. And I have said that for first overtone, the transition will be from nu equal to 0 to nu equal to 2. Since the v equals to 0 to v equals to 2. Since my v is equal to 0 in lower energy, so I have to just divide, I subtract this v nu equal to 0 from nu equal to 2. So your v nu 2 prime, nu 2 bar minus nu 0 bar will be, just put up the values, that's 5 by 2 chi e. So I am writing again the chi e. This will be nu e. 5 by 2 nu e bar minus 25 by 4 nu e bar chi e. Again nu 0, when I am putting this value minus half nu e bar, and this minus and minus again will become plus 1 by 4 nu e bar chi e bar. Just simple calculation, nu 5 by 2 minus 1 by 2, right? So I am writing one more line, nu e bar minus 1 by 2 nu e bar, this is 1 minus, you have to take this 25 by 4, not 251, this is 25, this is 25 by 4 minus 1 by 4. You can see here there is a plus and I have taken minus common. Yes. Now 5 by 2 minus 1 by 2, which will be 4 by 2. So 4 by 2 gives 2. That means 2 nu e bar, you can see it? Can you see it? Yes, no? Can you see it? Okay, I will take another page. That will be good for you, I think. So what I have told you that for fundamental vibration, I'm just reading the expression. For fundamental transition, what is the value? That nu 1 prime, nu 1 bar minus nu 0 bar comes to be how much? 2 nu, sorry, nu e bar minus 2 nu e bar x e bar will become nu e prime minus 2 nu e bar chi bar chi. And for first overtone, first overtone, its value was nu 2 bar minus nu 0 bar. What was the value? Just calculate it. Yeah, 5 by 2 nu e minus s2 and okay. 5 by 2 nu e bar minus 1 by 2 nu e bar minus 25 by 4 minus 1 by 4 nu e bar chi only, sorry, nu e bar chi. Now I am going to write what should be the value? This 5 by 2 minus 1 by 2, what will be the value? 2. 5 by 2 minus 1 by 2 will be 4 by 2, 4 by 2 means 2. So 2 nu e bar minus 25 by 4 minus 1 by 4, this will be 24 by 4, and 24 by 4 you know it's 6. So up to you understand up to this, that the energy of this fundamental vibration and what is be the energy of this first overtone. Do you have understand that?
Yes.
Okay, fine. Now I'm just doing some trick. Can I write it this way? I'm writing my 6 as 4 plus 2. I can easily write it. My 6 I can write it as 4 by 2. You can see for negative this taking this negative common, 4 nu e prime chi minus plus 2 nu e prime chi. So it will become 6 nu e time nu e prime, sorry, nu e bar chi. Okay. So I am taking these 2 common from the first 2 terms. 2 common will give me nu e bar. I can also take nu e bar common, but I am not taking this, minus 2 nu e bar chi, right? And this will become this one. So yeah. So what should be this value? Can you correlate this function? Hey, have you ever seen this? This nu e bar minus 2 nu e bar chi. Have you seen this? Is it the same thing, right? Nu e bar minus 2 nu e bar chi.
Yes, sir.
Exactly. So what is this is nothing but the wave number corresponds to fundamental transition. And in the question it was mentioned that it is nothing but 4000 centimeter inverse. So I'm just putting this 4000 because it was said that for fundamental transition the energy difference or the energy that is needed is nothing but 4000 centimeter inverse. So and since this corresponds to this fundamental transition, this one, so I am just putting all these as 400 minus 2 nu e bar chi. So my value will be 8000 minus 2 nu e bar chi. So this is my energy of first overtone. So you remember bit uh, before some minutes I have told you about qualitatively that if for anharmonic oscillator approximation your excited state energy will gradually decrease, the energy difference will gradually decrease. So your first overtone energy will be always less than your twice the fundamental vibrational energy. And I have also showed you that answer that it will be less than 8000 centimeter inverse. Now you can see this nu E bar, which is the vibrational frequency, it cannot be negative. Your chi E, which is anharmonicity constant, which is also cannot be negative. These two terms always positive. So there is a term 2 chi E nu E which will be decreased from this to the 8000. So the first value overtone frequency will always low than 8000. Do you understand that?
Yes, sir.
Energy will be less than 8000. How much less? It will be less by this factor 2 nu E bar chi. Okay. So this is your answer. Yeah. This is your answer. Taking it here. So you understand all this, how I have derived this? Hmm?
Yes, sir.
Okay. Okay. So next question. Which of the following band assignment either are wrong? That means you have to find out the incorrect answer. So here I have seen the transitions corresponds to overtone and hot band. Just you need to find which one is not overtone, which one is not hot band. So you can tell it. Is this already discussed in lecture number 26? Can you tell me the answer?
First and last.
Hmm?
First and last.
Yes. Yes. Exactly. So just brief. Overtone means transition from B equals to 0 state to any other than equals to 1. Okay. And hot band refers to, suppose in this case, this from V equal to 1 state to other. That means what is saying that for a hot band, you need to your molecule to be in the V equal to 1 state. From that, it can go to any other energy state. So for overtone, you need your ground state population will be high, so that your and you will be going from V equal to 0 to V equals to other states, no other than V equals to 1, because if it is going to V equals to 1 state, I will call it fundamental vibration. And for hot band, you need from V equals to 1 to any other state. So for your to remember it very clearly, I am just giving you a small trick to remember it, that if you are not confusing between these two. So suppose this name you can see here, this name is hot band. Okay, that means from this hot you can think of hot band means there is energy in the system, or you have given thermal energy, or you have heated the system. That means you have provided more molecules to the upper state, so the transition will happen from that state, upper state. Okay, so by this way you can remember this, that for hot band transition there is no transition from V equal to 0 state. This will be done going from this equals to 1 or any other higher excited state. So the actual answer is V equals to 0 to V equals to 2 is the first overtone, and V equals to 1 to V equal to is the first hot band. But in my question, it is saying that which one are wrong. So V equals to 1 to V equals to 2 is a overtone. No, it is a hot band, so it is wrong. V equals to 1 to V equals to 2 is a hot band. Yes, right. V equals to 0 to V equals to 2 is a overtone. Is it right? No. V is equal to 0 to V equal to 2 is overtone. Yes, this is the first overtone. V equals to 2 is equal to V equal to 0 to V equals to 2 is a hot band. No, this is not a hot band. This is a overtone. So these two will be the answers. Fine. Fine with this. We got it.
Yes, sir.
Okay. Okay. So another mathematical question that is saying that I have two molecules AB and B2 which have the same force constant and vibrating in. Okay, they have easy. They have easiest of tasks. So they have our task made very easy because it is simple harmonic motion. And two molecules are there, AB, another is B2. So, and also they is saying that the atomic weight of A is 5 times atomic weight of B. So they have find the ratio of the 0 point energies of AB and AB2, B2. Yeah, Vijaya, want to say something? Hello. Okay. Okay. So wait a minute. Yeah. So you are saying that the mass of A will be 5 times the mass of B. We have to find the ratio of the 0 point energy. So 0 point energy ratio, you have to find it for AB and B2. So you need to find, suppose I am writing 0 point energy as nu 0 bar for AB, which is the 0 point energy for AB, and I am writing nu 0 bar B2 for 0 point energy of B2. I can define it. What is the value of 0 point energy? On any system, what is the value of 0 point energy?
half h.
Half h nu, exactly. Half h nu of AB by half h nu of B2, right? Because it is a simple harmonic oscillator approximation, you can write this 0 point energy as half h nu. So half will cancel out, h will cancel out. You will left with mu AB by mu B2. Okay. And now the expression for nu was 1 by 2 pi root over k by mu, right? So nu of AB will be defined as 1 by 2 pi root over k by mu AB. I am not writing KAB because you have seen in the question it is already written that the molecules have the same force constant. That means K are same. So for B2, the same expression I can write as 1 by 2 pi root over K by mu of B2, right? So there is nu of AB, this is nu of B2. Now what I have to find is ratio of nu AB by nu B2. Now, okay. So what I have said you, here I have written that. So now I have to find nu AB. I've also done this today also. 1 by 2 pi root over K by mu AB divided by 1 by 2 pi root over of K by mu P2. So 1 by 1 by 2 pi 1 by 2 pi will cancel, and now I have also shown that taking this whole thing in the square root, this K will be cancelled out. So you will left with 1 by mu AB divided by 1 by mu B2. So you can write it simply as mu B2 by, sorry, you can write it as mu of B2 by mu of AB, right? So what is my final expression? My final expression is nu 0 bar AB by nu 0 bar B2. This will be mu B2 by mu B1, sorry, mu B2 by mu AB whole to the power half, right? So the next job is you have to find mu A2 AB and mu B2. So for this, I'm taking a new slide. There I will do the rest of, so I will do the rest of math here. And what I've got that mu 0 AB by mu 0 B2 will be equals to mu of B2 by mu of AB. This will be whole to the power half, right? So I have to find what is mu of B2 first of all. Next I have to find what is mu of AB. If I have to find this two, I have to put that in the equation. Then I will find nu 0 AB by nu 0 B2. Now I am going one by one. First, what will be my mu of B2? Mu of B2 is mass of B plus into mass of B by mass of B plus mass of B. You know this, that this reduced mass, I'm writing it here. So what will be for mu AB? Sorry, this is into, okay, plus minus. So this will be MA into MB. So it was discussed in the earlier classes that reduced mass is derived from this reduced mass mu is derived as M1 M2 by M1 plus M2. Here the same thing, MB into MB by MB plus MB. For AB it is MA into AB by MA plus ME MB. Now what is the value? This is MB square. MB into MB will be MB square, and this will be MB plus MB. That will be 2 MB. So 1 MB will be cancelled out. So you will left with MB by 2. And for this, I'm just writing this one. Okay, I'm not just cancelling anything. I'll do it in the later stage. You'll understand. So I have got value of mu B2 as MB by 2, and I've also got mu AB as MA MB by MA plus B. Now you have to put here. So what will be my mu B2? Mu B2 will be MB2 by 2. And what will be my mu AB? This is in the denominator, so it will be MA into MB divided by it will be going up because mu may be in the lower side, so it will become MA plus MB, right? So for this clarification, I am just putting a bracket. So why I have, okay, so it is not B2, it is B, mass of B. So it is B, MB, MB will cancel out. That's why I have told you not to do that, but you will need to do now it. So it will become MA plus MB divided by 2MA. That's where we have stuck because we need to find. So we have done all the mathematics. We have just stuck with the atomic masses of MA and MB. We have to find a correlation between this MA and MB, then we will got our answer. So if you can remember, there was a condition that MB, what was the condition? The condition is given as your MA will be 5 times of MB. Now I am going to put that. So the condition was MA is equals to 5 times of MB. You just put it here. So what will become? It will become M. So sorry. So MA will become 5 times MB plus there will be MB. There will be 2 into 5 MB because MA is 5 times of NB. I have written it in the left side, left top side. So what will be the value? 5 plus 1, 6. So this will be become, sorry, there will be a half term here. Yeah. So 6 MB by 5 into 2, it will be 10 MB. So if you do a simplification, it will get this 2 will, you can divide both side by 2. So we will be left with 3 by 5 and MB will be cancelled out. So what is the ratio of these 0 point energies? The ratio of the 0 point energies are root over 3 by 5. You understand that how I have calculated this?
Yes,
Yes, is easy.
yes,
Okay. So your correct answer will be root over 3 by 5. Okay.
yes.
Okay. So yeah, this is the next question. This is a very straightforward question. The energy gap between fifth and sixth level in simple harmonic oscillator model. It is again mentioning that it is simple harmonic oscillator model, which is making your life too much simple. Simple harmonic oscillator model. So you have to find the energy gap between two successive energy levels. Suppose my E for V, quantum number V is V plus half h nu, and I have told you that for simple harmonic oscillator, what is the energy difference between two successive states?
H nu.
Only h nu, exactly. Because if you put this V plus 1, suppose I am putting this V plus 1, successive level means from V to V plus 1. Okay. So V plus 1 minus the V, will see this V plus 1 plus half h nu minus V plus half h nu. So just you will get VH nu plus H nu plus H nu by 2 minus VH nu minus half H nu. So half H nu, half H nu will be cancelled out. VH nu will cancel out. So you will left with this expression only H nu. So now can you tell me what should be the energy difference between fifth and sixth energy level?
Half H nu.
Why?
Nu by 2.
Why? I've said you that the energy difference between two states is h nu. Is there any mention of this quantum number V? The energy difference between two states is h nu. Is there any mention of V? Hmm?
No.
No. So it is independent of V. So if there is, suppose someone is asking for simple harmonic oscillator, what is the energy difference between V equals to 100 level and V equals to 101 level? So what will be the answer?
One.
Hmm?
One.
No, it will be h nu only. Okay. So any two successive levels, the energy difference is always h nu. Whatever be the level, be it 1000, 10,000, whatever be the level, for a simple harmonic model, simple harmonic oscillator model, always the energy difference between two states is h nu. So what will be the gap between fifth and sixth level? It will always be h nu. Okay. So for harmonic oscillator, the energy gap between two successive levels is h nu. Got it?
Yes.
Yes. Okay. So next question. So with increase of temperature, what would be happen? Suppose what here in question it is a very quality question. So what will happen with the hot band and what will happen with the overtone? When T increases, what will be the fate of these two things? The intensity of hot band will increase or decrease, and what will be the intensity of this overtone? Will it increase or decrease or both remain same? Both will decrease. What should be the answer? With increase of temperature. Suppose I am pouring heat in the system. So what will be the change in the hot band and overtone? So do you know what temperature does to a system when you are giving heat?
Intensity of both bands will decrease. I don't think this is correct, but I'm thinking.
Okay, okay, I'll explain. Okay. So what happens actually that if you are increasing temperature or if you are giving heat or kind of something to the system that will increase the temperature, actually the population of the level changes. Population of the level changes. Okay. So actually, I am giving heat or I am giving temperature. I am using temperature for a system. That means I am just changing the population of the system. Suppose my all in the room temperature, my most of the population will be for V equal to 0 state, room temperature, right? Most of my molecules will be in the ground state at room temperature when there is no heat. Now, if you are increasing heat, when T increases, so population of V equals to 0 will increase or decrease?
Will increase.
Hmm?
In.
Will increase. Will increase.
No. When you are, suppose I have 100 molecules in the V equal to 0 state. Okay. Now I am giving temperature to the system. So what will happen? Suppose there I have 100 molecules. Out of this 70 will be there in the ground state and 30 will be go to the excited state. Okay. Now you are giving more temperature. Now 50 molecules will go to the excited state, 50 molecules will be in the ground state. So in increased temperature, this population of V equals to 0 will decrease, right? But the population of V equal to 1, right? So the population of V equal to 0, that is the ground vibrational state, will decrease with increase of temperature, but the population of the upper excited state will increase with temperature. Up to this point, it is correct, or it is you have understand that?
Sir, I'm not hearing properly. So, if you are increasing temperature, population.
You can change actually using temperature. You can change the population. Okay. So suppose I have 100 molecules in the V equal to 0 state. So in the room temperature, you have 100 molecules in the V equal to 0 state. Now
Yes,
you are
yes.
giving temperature. So
Temperature,
what will
then it
happen?
will be
Your 70 molecules will
ground
be there.
state will.
Yeah, ground state population will be low because more number of molecules will try to go to the excited state. They are given energy. So they will cross the barrier and they will go to the excited state. Okay. So as
Okay,
you are giving this more temperature, more number of molecules will go to the excited state.
okay.
So what will change the population? The population of
Yes,
V
pop.
equal to 0 will decrease, right?
Yes, yes, yes.
But the population of V equals to 1, that is the upper excited state, that will increase,
Yes,
right?
yes. Ground state will decrease and upper state will increase. Okay, sir.
Exactly, population of the upper state will increase.
Yes, yes.
Now, you know, this overtone is the transition from which level? V equal to 0 to V equals to 2. Suppose I am taking V equal to 0 to V equal to 2. 3, 4, anything will be possible. For the simple case, I'm just saying that overturn is a transition from V equals to 0 to V equals to 2 state. Okay. So what will happen? Since with increase of temperature, the population of your V equals to 0 level will decrease. So your intensity overtone will, what will happen to the intensity of the overtone? Intensity will increase or decrease?
increase.
No.
Will decrease.
Exactly. Intensity depends how many particles are there in your state. Suppose if your V equals to 0, there is 100 molecules. Okay. So intensity and suppose after some time when you are giving temperature, the population is decreased and from 100 molecules there are now 60 molecules in the ground state. So what will happen? Your intensity will decrease because less number of molecules is available in the V equal to 0 state. So for overturn transition, which is V equal to 0 to V equal to 2 state, suppose for this case, since your V equal to 0 population is gradually decreasing, so your intensity will decrease, right?
Yes, decrease.
Exactly. Next is hot band. So hot band is the transition from V equals to 1 or V equals to higher level to any high level. Suppose from V equals to 1 to V equals to 2.
Two. Okay.
So what I have said, if you are increasing the temperature, your population of V equals to 1 state will
Changing.
changing, that is increasing or decreasing?
That is ground state decreasing and
Excited state
excited state increasing.
increasing. That means V equals to 1 is the excited state. So the population of excited state is increasing. That means your intensity of hot band will will
Decrease.
increase.
How it will increase?
Why will not increase? Because your population in V equal to 1 level is increasing. The same thing for overtone. Suppose for overtone you have four population. Your population in V equals to 0 to V equals to 2 state transition. Your population in V equal to 0 is decreasing. So intensity is decreasing. Less number of molecule in the V equal to 0 state. Now, when you are giving temperature, more number of molecules in the V equal to 1 state. And hot band transition occurs from V equal to 1 state. In V equals to 1 state, you will have more number of molecules. So your intensity
Okay.
will be always
Yes, more.
increase. Because more number of molecules, you are creating more number of molecules in the V equal to 1 state.
But finally, we will be considering intensity of excited state only, no, sir.
Hmm?
So finally, we will consider excited state intensity only, right?
Yes. So actually
So
for
from the V1 to O2 it is coming. So 2 intensity we have to take, right?
2 intensity means
So hot band transition from V1 to V2. So V1 is ground state and V2 is excited state.
no, it is not ground state.
Oh,
Oh, V equals to 0 state is the ground state. Okay. So okay, I am drawing it. You will understand this clearly. This is V equals to 0 state. Okay. This is your ground state. This is
yes,
your
yes,
first
yes.
excited state.
I'm
This
sorry.
is your
Yes,
second
yes.
excited state.
Yes,
Okay.
this is third excited
So
state.
at room temperature, more number of molecules are here. Okay.
Yes, yes, yes.
Yeah. So more number of molecules are here. Okay. You
Yes,
are giving
yes.
temperature. This population was very low at room temperature. Very low. You are giving
Yes.
temperature. More number of population will be here. Okay.
Transition is occurring.
Okay. Yes. Exactly. And your hot band corresponds to this transition. So if your more
So,
number of molecules will be here, so more intensity will be here for the hot band, right?
okay. Okay.
And since this population is decreasing and your overtone corresponds to this transition,
Yes,
this
it is
intensity
decreased.
of overtone will decrease.
Okay.
Understand everybody?
Yes, 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 I understand.
So this is the written here. The hot band refers to the transition from excited state, whereas overtones are the transition from the ground state. With increase of temperature, the population of ground state will decrease and that of the excited state will increase. So the answer will be your intensity of hot band will increase,
Will increase and intensity of
intensity of
overtone will
overtone
decrease.
decrease. Understand that?
Yes.
Okay, fine. Okay. So I'm going to the final question of today. Molecule A and B have following properties. Identify the ration or ratio. This is not ration. This is ratio of fundamental vibrational frequency. That is, we need to find mu A by mu B. This is a very straightforward question. What will be the answer? And it is the condition mu A is equals to 16 mu B. Sorry, I can't hear you. 1 by 2,
4, 4.
1 by 4. Okay. So you will find this reference in lecture number 23 and the fundamental vibrational frequency. I'm writing it again 1 by 2 pi, sorry, 1 by 2 pi root over of A by mu. Okay. So if you taking the ratio of mu A by mu B, I have shown you that this 1 by 2 pi term will always cancel out. Okay. So okay, I am writing it again. A by mu A by 1 by 2 pi root over of Kb by mu B. So this 1 by 2 pi will cancel out. You will left with this thing that Ka by mu A into this Kb. This thing will be just reversed mu B by Kb. Okay. So just you just put these values. Your Ka you write it Ka into your mu B. You write it mu B. You have mu A, and it is written that mu A is the 16th mu B. So I am writing it as 16 of mu B. And this Kb, it is also mentioned here that Ka is Kb. Ka and Kb are same. So I am just replacing Kb with K. Okay. So this Ka will cancel out. Mu B will cancel out. So I will left with this term 1 by root over of 1 by 16. And you know this value is 1 by 4. So what will be the value of mu A by mu B? This will be is equals to 1 by 4. So which one is the correct answer? This is the correct answer. So I have solved math related to this also. So have you understand that?
Yes, sir, understood. But in
Hmm.
fifth assignment, I have submitted and
Hmm.
I saw the answers and
Hmm.
fifth and sixth gap
Yeah, yeah, yeah.
yeah, that is the H nu is correct only, but
Hmm.
there they were starting it is the incorrect answer
No,
and
H new is the
there
correct answer. Yeah, I've seen that
H nu,
also.
yes,
Yes, but your actual answer will be H new. I've seen
yes,
that
sir,
also.
H
H nu
nu,
by 2 was later there, but your actual answer will be H new because any
yes,
genetic between any two level will be H new. Whether it is fifth or
H nu.
sixth, seventh or eighth, anything.
Yes, there they have given H nu by 2 is a correct answer.
No, no, the actual answer will be H new.
Then they will not correct, sir.
No, I don't know that what they will do. But you know the correct answer. Just in your exam, you can write it.
Okay, okay, sir.
Hmm.
Okay. Thank you, thank you.
Okay. Anybody have any more questions? So, do anybody have any more questions? Okay, I don't think anybody have. So, I'm closing this session. In the recording.